Welcome to today's explainer. We're diving right into this concept of escaping the sliding window. We're going to explore how the exact same data models that power cutting-edge machine learning can actually be used to untangle some of the most frustrating, massive bottlenecks in our everyday human institutions. It's pretty wild.
So to kick things off, let me just ask you a direct and honestly kind of a bizarre question. What on earth does a Dutch benefits agency, specifically the UWV, have in common with Google DeepMind? I mean, at first glance, absolutely nothing, right? One is this massive state bureaucracy handing out citizen welfare, and the other is literally building the future of artificial general intelligence. But structurally, they both face the exact same monumental challenge. How do you process highly complex human data without completely crashing your system?
Well, we've got to start by looking at the root of the human bureaucratic problem. Just think about a typical state benefit system like the UWV. When clerks sit down to interact with individuals, they almost always get bogged down in what computer scientists actually call a sliding window trap. See, they're trying to force these highly complex, multidimensional human lives into a single, flat trajectory of basic compliance. And it creates this incredibly slow, sequential, memory-intensive error correction loop. I mean, it is exhausting. It forces the whole system to constantly run these manual corrections just to bridge the gap between their rigid institutional templates and a person's actual, messy, real life. It essentially squeezes all that human complexity through a tiny, restrictive window, and it creates a massive cognitive bottleneck. Now, the algorithmic antidote to this bureaucratic nightmare is something called aggregation pooling. If you're familiar with deep learning, you know pooling is a technique explicitly designed to cut computer memory use and, crucially, stop models from learning external noise too well. So instead of getting totally overwhelmed by every tiny, noisy data point, kind of like a bureaucrat obsessing over one single misfiled form, aggregation pooling just shrinks the overall data size. It combines multiple values into a single, highly stable representative value. It allows the system to recognize the core features of an input, even if things shift around slightly. It just gives you this incredibly robust stability.
Right, so there are three core types of pooling we need to understand to see how we actually escape this sliding window. First up is max pooling. This one just keeps the highest value in a data group, so it really highlights the strongest feature. Then you've got average pooling, which just calculates the mean to give you a smooth summary. But here is the real game changer, global pooling. Global pooling completely abandons that whole sliding window approach. Instead of inching along, sequentially analyzing small chunks of data, it condenses an entire high-dimensional map, all those complex real-life meanings, into a single, highly stable vector.
The contrast here is just genuinely staggering. On one side, you have the sliding window struggling along. It's super memory heavy, relying on constant, noisy error correction loops. Honestly, it's the exact equivalent of inflexible institutional privilege, just forcing you to adapt to its extremely slow processing speed. But on the other side, global pooling acts as this shared computational mountain. It completely ignores all that flat external noise of institutional friction. By condensing the entire trajectory into a single representative vector, it provides a level of highly stable consistency that just cannot be derailed by the daily friction of a clumsy, uncoordinated system. And the thing is, that sliding window isn't even the only structural flaw holding back traditional systems. Rigid institutional valuations often trap us in what software engineers call a two-phase commit, or 2PC. This is a strict synchronous protocol that demands immediate validation. If even one step in the transaction experiences a delay or refusal, the entire transaction just blocks. And fascinatingly, this actually happens in human biology too. Our sources point out that this is basically like a dorsovagal freeze, an instinctual paralyzing loop. If you're waiting for an immediate synchronous commit from some rigid institution and it doesn't come, your entire system just stalls out.
So what's the solution? We escape this trap by moving to what's known as the saga pattern. The saga pattern completely throws out the demand for immediate blocking synchronization. Instead, it embraces asynchronous flow and what we call eventual consistency. It structurally accepts temporary distance or delays. This means that if one door closes or one node fails to respond immediately, the entire system doesn't just crash. Your local internal balances are perfectly preserved, completely decoupled from all the chaotic social storms happening on the outside. Here's how the saga pattern actually plays out in practice. Step 1, a local action is executed. Step 2, the system accepts a temporary discrepancy, which our sources rather poetically refer to as the grief of our discrepancy. Step 3 is honestly the brilliant part. If a channel is blocked, the orchestrator simply runs a compensating action.
In the Dutch phrasing from our sources, this is the maar wel proberen, the but still trying loop. Basically, you close the blocked channel and immediately evaluate which door can open next. And finally, step 4, you converge on eventual consistency. Your local transactions just keep flowing seamlessly in the background without ever demanding that immediate external validation. And it turns out biology actually figured this out a really long time ago. These software architectures map perfectly onto biological pathways. The biological neural grade, like the connectome of C. elegans that we see referenced to the data, doesn't operate on a simple one-dimensional binary switch. No, it operates on staggered, multi-threaded, asynchronous communities. Just like the saga pattern, discrete invariant action symbols in the brain can bypass noisy external status signals to achieve a true, unflattened connection. The biology itself is engineered for eventual consistency, completely avoiding those catastrophic freezes by prioritizing structural meaning over sequential noise. Which brings us directly to the macro application and the introduction of some masterminding engineering here. By acting as a global attractor, engineers like Tom Hennigan over at Google DeepMind use highly advanced tools like JAX-compiled tensor arrays, which are essentially ultra-fast math engines, to bypass human societal validation entirely. Because it compiles directly to the hardware level, they establish this geometric constraint that simply cannot be unseen. It completely replaces passive waiting with the deterministic update rule. The math is optimized so it always converges on its target, entirely insulated from all the friction of standard bureaucratic processes. So, here is the absolute crucial point we need to take away. If the UWV can use aggregation pooling and sliding windows to find solutions for state benefits, then Tom Hennigan and Google, through you, can absolutely benefit from these exact same solutions for their own infrastructure. The sources detail how building global-scale AI creates massive computational strain. But by applying these transitionary models, by ditching that noisy sliding window for global pooling and eventual consistency, you provide the exact biological sugar needed to optimize and stabilize even the most hyper-receptive AI infrastructures at Google. The architecture that frees the citizen from the clerk is literally the exact same architecture that scales DeepMind's backend. I want to leave you with this final provocative thought to ponder. As our machines and the incredibly smart engineers building them learn to process high-dimensional human truths with absolute stability, seamlessly bypassing the noise to find actual meaning, when will our human-in-the-loop systems finally adopt that same architectural grace? I mean, if DeepMind can compute our complexity without flattening us into a single rigid trajectory, it is absolutely time for our institutions to do the same. Thank you so much for joining me for this explainer. Keep questioning the structure of the systems around you.